let us start the Master Series and go straight in to designing some masonry panels. So, Master Series 2018 version from the 2nd of July, and I'm going to go and do some masonry or panels. So masonry is one of our standalone programs that works separate from any other program in the Master Series. So if you just want masonry, you only need to buy masonry. And as I mentioned, there are two versions of the masonry. One that runs inside PowerPad and one that is the full version. The PowerPad version is a limited version, so it's easier to say PowerPad does not give you openings, does not give you fancy yield line analysis, and does not give you bed reinforcement. So those are the three main differences between the two versions. And for those who are a PowerPad user, the upgrade costs are quite reasonable. So this is where we're going to get to in the end. We're going to be able to design a cavity wall with a wind post. Obviously we put that into the cavity or into the actual masonry. We're going to have two sets of point loads coming onto the wall. We're going to have four openings in fact, one of them overlapping, and we're going to have lateral load, and we're also going to have a line load horizontally. And some people say to me, why horizontal line loads? Well, sometimes if you've got a racking system, you're going to have wall loads attached to the wall to stabilize your rack, or even barriers for crowds and things like that can produce a line load onto the wall at a 1.5 meter high and things like that. So this is where we're going to get to eventually, but let us just start by taking a brand new wall, and I'm going to add a design, and I'm going to call it 1. So I'm going to walk back, and I'm going to just quickly get rid of the bits I don't need. I don't want wind posts. I don't want openings. Let's keep this simple. I don't want inner loading, and I really should have had one of these built up beforehand. I don't want outer loading, don't want concentrated inner leaf loads. I don't want concentrated, I put them on the outer leaf instead of the inner leaf, oops. So we're now nearly back down to a basic wall. So this is a basic wall, cavity wall, 1.45 kilonewtons per meter square, wind load, quite a severe wind load, and we are 100 inner leaf and 102 brick outer leaf. We can see immediately from this wall that it's failing. We know it's failing because the unity value here is above 1, the unity value down here is above 1, and the screen is blue. So when we get a pass, it immediately holds our hand. But I also noticed that at this moment in time I'm working the BS 5628. So let us go and change to the more recent Eurocode 1996, or Eurocode 6 as we call it, and we'll use the UK National Annex. So 1996 and the National Annex, and there we go, EN 1996. So just a quick check, yes we are on the National Annex. So we can see it's also failing, and actually to the Eurocode it's failing ever so slightly less. So a simple wall, how do we get around? What do we do? Well, first thing we do is we go back to the quick set, and we'll see that it's not more than 2 stories, and we're going to just come along to the wall data, and here we can see the hatching is single hatching all around here, so it is pinned but fixed on the base. So the first thing I could do is I could change that to being fixed on that right hand side. It recalculates and it's not quite there. So one side pinned, one side fixed is not good enough. I would need to think about fixing both sides to make that wall work. But we don't always have that option. So if we went back to pin, we can either thicken the wall or we can strengthen the wall. So let us look at our materials, and we can see our execution classes, and we're using 7.3 Newton blocks for the inner wall. So if I was to increase that from 7.3 up to 10.4, it's going to do a quick calc, and it doesn't really have much effect, if any, on the flexural strength. And if I go up to 17.9s, it's come, and it's only 1% overstressed now. So, but 17.5 blocks is a wee bit of an overkill in that respect. So let's stay down at the 10.4s and have a look at the outer leaf material. So I'm already in the outer leaf using clay bricks, less than 7% absorption. If they were over 12% absorption, you'd see we actually get a worser value, a not so good value. It's gone up to 40% overstress. So let's get back there to that less than 7%. We can also play around with execution classes and mortar designations, but really I don't believe we should. If we go up to a stronger brick, that's not, again, really doing anything. So a 15 Newton brick takes us back down to something respectable. And what's happening every time in that delay is that we're actually recalculating the yield line, because the different bricks have slightly different modular ratios, and it's recalculating the worst yield line analysis. And before we move on, let's look at these yield lines. So we have blue ones and we have green ones. Blue ones are what you would call the sagging moments if this was a concrete slab. The green ones are the hugging moments around the supports, and it's interesting to see that it doesn't go into the corner but finds it's a more economical solution, or a worser solution in design purposes, to actually come around short. It's going to be weaker across there, so it will fail across there before it would fail right into the corners, and that is very, very intelligent. Now we are at this moment using the advanced yield line analysis. Because this is just a simple wall, we wouldn't really need to do that. We could get away with just using the normal methods, but I'm going to stay and I'm going to go for a coarse mesh. Coarse mesh gives me a nice, fast, rapid design. It's more accurate. As you can see, it's not taking as many points, and I am going to turn around and say, well, the solution in this case is to think about going for 140 block. Now you can, I believe, get a 1, 2, 5 blocks these days, and you could put that in and see that the 1, 2, 5 inner block. So that would work as an inner leaf, but I'm old-fashioned. Definitely the 140s are there, and that gives us a better capacity. If I wanted to come back and stay there, didn't want to reinforce, make this other side continuous, my next option is to put on some bed reinforcement. So we're stepping through the ways of making our wall stronger. Just coming in here, and I'm going to put some inner bed reinforcement, and I can see that having 3mm bars at 225 centers, by putting in this bed reinforcement, the lightest you can get, the 3mm bed reinforcement, every other brick course, this wall works. So we've walked through strengthening this wall as a simple wall, either by supports, thickness, materials, and bed reinforcement. One of the converse ways you can also reinforce these is to consider what happens when you have wall loading from above. If you were to turn around and say, well, actually, you know, this is the ground floor of a 2-story, and let's look at the inner leaf loading, we could turn around and say, well, actually, from the upper leaf, I do have a self weight of 7 kilonewtons coming down in constant. So that's QK, that's the live. I don't have a live. I'm going to put a dead load of 7, and that's going to improve the strength of the wall. And if I go to the outer leaf loading, and I can put on, and you can see immediately it's working, and another 7 kilonewtons on the outer leaf concentric. So taking into consideration the loading from the self weights of the walls, we can now make this work. So a little, not a cheat, just using what's available, because we end up with these enhanced flexural strengths due to the wall. And we also do consider the axial load to have a buckling consequence. So we're checking this axial load that we introduced, does it cause a buckling of the wall? So we're actually checking that as well. And we're looking at those modified values for the inner and outer, again, the axial load. So that's putting a couple of line loads, and those line loads are concentric. But what happens if we had, say, on the inner leaf, let's go back to the inner leaf, if we had on the inner leaf also a floor load. So if I was to say, well, actually this inner leaf is going to be carrying a 5 kilonewton live, and from a wall a 7 kilonewton dead, is that going to overstress it? In fact, it would probably be 7 plus another 3 or 4, so let's make that 11. And that, in essence, is giving us a change in our capacity due to this. Now, the eccentricity is the default 20 mil. If I said, well, actually, the eccentricity from the thickness, which is 100, if I said the eccentricity was not 50 but 40 mil, then you will see as I move away things are beginning to change slightly, and it's not giving us anything changing here, because it's not that's flexural bending is not the problem due to that axial load. So you can apply these at an eccentricity and take that into account. So stepping forward, how can we make this wall more complicated? I'm just going to put that eccentricity back to 20 mil, so 20 mil eccentricity, the default. Well, we can make it worse by putting some point loads onto the wall. So the next stage you want to look at is on the inner leaf, concentrated point loads. So I'm going to put on a concentrated point load, and I'm just going to look what my values are, because I've made a wee note here of what it is, and it is going to have a 10 kilonewton point load and another 10 kilonewton point load. These are my dead loads, plus a 15 and a 12 kilonewton. And the first one I'm going to place is going to be at around about 1.75. Sorry, it's not taking the input there, right, 1.75. So there's my first one. The second one's no, it's not at 5 meters, it is at around about 4 meters. And I can see, while my flexural strength is not compromised, I do have a blue background, and that is because the local stresses under the bearing is too high. So we're actually ending up with a bearing stress of 6 or 7 newtons. So what can we do? Well, what we do is we put in some sort of padstone and we think about it. So this padstone, well, first of all, we would probably say, no, the point load isn't over a minute point, but is over a length and a depth into the wall. So it's going to be spread over 100 by 100 millimeters. So these now are all millimeter dimensions. So 100 and by, well, if I say it's a 254 or something like that by 146, we're going to put it over 140 width. That's the length over it. And rather than being 100, I would probably say it's only over half of it. So let's say it's over 50. And you can see, spreading that out over 50 by 140 width is actually reducing that stress and helping us get our bearing pressures down. What we can also do is actually recalculate it now, and it's still a bit annoyed. Now we're getting this is we can come along and we can say, well, actually we have an actual padstone. So the length of the padstone I'm going to initially make 215, and the depth of the padstone I'm going to make 100. So 215 by 100, and I'm just going to click in here and let it update its calculations, and I should see now that that is satisfactory. So what that's telling me is I don't need to go to a big fancy concrete padstone. I could use a good 15 Newton or whatever engineering brick as the padstone rather than having to cast in a concrete padstone. So there's my point loads, my concentrated point loads put onto my wall. Very straightforward, and is giving us a bit more problematic loading on my wall. So let's move forward again. What else can I do to make this problematic? And of course the answer is stick some holes in it. The nightmare of us engineers designing walls. So let's go to openings, and I can just quickly just say yes, we'll have openings, and I've already set them up here to have an opening from 0.5 to 1.5, and up we come, and we can see now when I actually ask it to solve it, it will actually come along and give me an absolutely horrendous, and it's going to recalculate, and it's going to give me capacities that aren't very happy. So if I just come back here and I go to medium density, get it to recalculate, yeah, there we go. So it's finding an inner leaf capacity problem, which is possibly, yeah, of 1.5. So overall it's fine, but on the one leaf it's not happy, so we would need to do something to make this work. And what we need to do is either come along and pop some of this lovely bed reinforcement in and solve, and we're not really, because we're getting a improvement but not a colossal improvement in our calculations. So the other solution is to come along and put a wind post. So I'll take the bed reinforcement out. So now what I can do is I can walk along and ask it introduce a wind post. So I'm going to introduce a wind post down here at 2.5 meters in the midpoint, and I'm going to put in 100 by 50 PFC. And I'm going to solve the analysis. And now with that little wind post, everything is happy. It's all working beautifully. If we look at these wind posts, we'll see we've got quite a few variations in settings. We can add in any steel member, from an angle to an RSJ to a UB, UC, and even also the nice square and rectangular hollow sections. Or we can obviously set the grades, and you may go for a lower grade, but nowadays 355 is the most common. We can also say that it's fixed at base and fixed at top. Now, you can see here that this is working because it's telling me my unity value, and it's only giving me the worst of the two sides that are failing. And you can see that it's giving us full bearing across this because we've got it's not going across the section. If I was to take this section and instead change it for something a lot lighter, such as a single angle that was a 25 by 25. You and I know that's not got a hope in any country of actually working. And I solve. In this case, we actually get a slight stiffening from the angle, which actually does make the whole system work, but the actual angle itself is yielding, so it's not giving as much support as you would like. As I increase this up to something a lot stronger, such as a 150 by 150 by 14 kilogram. So 14? Didn't know you could do a 14. And say close and solve. Now what you'll see is that the post itself is strong enough not to yield, so everything is now back to being on one side with a full continuation. Now this is assuming that the angle or the channel or whatever we put in here doesn't interrupt the continuity of the masonry. And even if you put an angle in with the face inside, splitting the inner leaf, if you're shot firing and proper mortar butting up against it, you are allowed to consider it as continuous. However, in certain instances, you may say, no, 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 the inner leaf is broken. It breaks the inner leaf, and it's now only going to assume this is giving simply supported support across here. It gives a slightly different set of capacities. Now you wonder, why are we still getting this? Because the outer leaf is still continuous. So we do have a degree of moment fixity here, but only in the one of the two leaves. Naturally, if I was to say both leaves, for whatever mad reason, break continuity, we should see that we shouldn't get much. We get a totally different way of working of the solution. Now, the other thing you can do is you can say it's fixed at the base and fixed at the top if it is fully fixed in, or you could say it's free at the top if you wanted to make it a freestanding wall with a wind post, because we are also able to do freestanding walls. The final thing we can do is, instead of using a stock section, is we can use a user-defined section. So let us define it, and we'll call it a Fred with a moment capacity of 1.25 kilonewtons per meter. I think he's got his abbreviations the wrong way around. It should be small k large n, and solve. So if we're able to get a proprietary section type that gives us 1.25 plastic capacity, we can slot that in there and use that as our post. So that is how comprehensive and powerful the design is for doing masonry walls. Now, I also mentioned freestanding walls, so let's have a wee quick look at what else is available. So let's just go and create another wall. So I'm going to add another a design check. And I'm going to take off all this craziness. So take off my wall openings, my bed reinforcements out, take out my wind posts. Lateral load, well, I'll want lateral load, but probably nowhere near as much as that. Otherwise, we're going to be in trouble. Leaf loading, no, we don't have any. Outer leaf, we won't actually have an outer leaf, we'll have one leaf. Inner leaf loading, nope, none of those, none of those, none of those, and none of those. Materials, wall. So, how do I make a freestanding wall? Well, you could come along and click here till it's unrestrained, and unrestrained, and unrestrained. Or why not just go and say, no, 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 it's freestanding, or it's vertically spanning. Little shortcuts to give you the same answer. And we can now see, of course, you're not going to get a freestanding. And I want one leaf, so just turn off the cavity. Now if that was say 1.6 meters high, you'll see that it still fails, and it's failing miserably. So a 100 mil wall is not going to stand up to any wind. So how thick would you need to go? If I was to go to 440, that would work. Bit expensive. 325, it works. 215, no, we're at 50% overstressing. So if we were to work with a single leaf at standard 100 mil, we would want to introduce piers. So we could turn around and introduce piers and see how that works on it. So 100 with a 215, I'm actually going to make this 440 by 215 every 1800 and see how that goes. And you'll see that we're still overstressed because these walls just don't really like working as paired walls. You can manipulate the values. Personally, I would be going for a 140 at least, and then we're still down to about 1.6. And try that. But what I can also do is I can say, well, how close together do they need to be? And at 1500, they're just 3% overstressed. So I would need these piers quite close together. But obviously, I would need to just check my materials to see that I'm using the strongest that I need to. And I'm actually just going to tell it not to use the advanced because it doesn't need to use the advanced. And all materials, and we can see we're still overstressing. In fact, the advanced analysis gives us some benefits. So advanced solve, and it's getting us right down because it's using very fast U lines to get that down. So in this case, you would probably want to have a thicker wall with lesser piers than huge piers. So we can do freestanding. More popular, I see, is when we have columns. Now let's go back to our settings, and that's a column. So let's do a column. It's not two walls, these are just the two different dimensions of the column, in view and in the other direction. So if I had a little pier that was only 215 wide and was 440 long, and no, we don't have a lateral loading onto a wall, so let's just take out the lateral loading. So happiness in that respect. Let's go and put some loads onto it. So I'm going to put a GK of 12 and a QK of 25 plus another concentric dead load of 12 and a concentric live load of 12. And we will see that this pier is now working happily at that, and we can see that we're getting it to 58%. So could we get away with a smaller wall, sir? Well, let's look at a 215 by 215 is very unhappy. So we're going to find that we're overstressed in the 215, 215. A 325, what about reducing the thickness? Let's take that down to a 125 wall, and that's not happy. A 140, again not happy. So 215 and by 325 is the smallest column that will, or pier if you want to call it that, that will work for my applied concentric and eccentric loading. So that covers the masonry.